types. It's my pleasure to introduce the first speaker to you, Evan Carvalho, and he'll talk about higher inductive types in cubical computational type theory.
Thank you. Shall I go? Okay. Hello, everyone. So this talk is about taking cubical type theory, which is a dependent type theory with a univalent, proof-relevant internal equality, and extending it with indexed higher inductive types, which roughly give us a notion of quotient types for this equality and indexed inductive types that respect this equality. So let me start by explaining this slogan for cubical type theory, and we might name this slogan higher type theory. This is a concept that's sort of been introduced by Audi and Warren and by Voevodsky, and so let me go through what I mean by each of these words. So first, by internal, what I mean is whenever we have a pair of elements of a type, we want to have a type of proofs that they are equal. And I'm going to call this suggestively a path type. And for this to be an equality, what we want roughly is whenever two terms are equal, we can transfer constructions between them. So if something holds of M0 and M0 is equal to M1, then that same thing holds of M1. So that's the basic stuff for equality. And now our big ask is going to be for this to be univalent. And so this is Voevodsky's axiom that says when two types are isomorphic, we can regard them as equal. And so once we accept that principle, we're kind of forced into this last thing, the proof relevance, because an isomorphism is a kind of data. And in particular, there can be many different isomorphisms between the same pair of types. So we want to consider in general that two terms can be equal in different ways, and we want to regard those equalities as a kind of data. And so this specification for a type theory is axiomatized by homotopy type theory. But what we're interested in is a computational realization of that specification. And so for that, we turn to cubical type theory. This has been developed sort of in two main lines. There's the work of Cohen, Kokan, Huber, and Mortberg, and then by Angiuli, Favonia, and Harper. And our work builds on the second of those two. But in either case, the idea is to come up with a computational interpretation of higher type theory using what are called dimension variables. So the basic idea is that we take the judgments of type theory, A is a type, M is an A, and we tack on this context of dimension variables. And each of these variables is to be thought of as ranging in the unit interval between 0 and 1. And so we can substitute special constants 0 or 1 for them. And so as M here ranges over some xi, it draws out a line in the type A connecting the endpoints M with 0 for xi and M with 1 for xi. And so that's going to be our notion of path. And we can internalize that using a path type, which looks a lot like a function type. So if I have a term M, which varies in a dimension x, then I can abstract over x to get a path from M with 0 for x to M with 1 for x. And likewise, if I have a path, I can apply it at some dimension term, which will be either a variable or a 0 or 1. And operationally, too, these behave just like functions. Okay, so that gives me an internal something. And in order to make this an equality, we introduce an operation called coercion. So what this does is, if we have a line of types, a type varying in a dimension variable, then we can coerce anything that lives on one endpoint of this line to something on the other endpoint of this line. And actually, we want to generalize this a little bit. So if we have something living at any point along this line of types, we can coerce it anywhere else on that line. And now, in order for everything to be computational, we have to explain how to implement this coercion. And in order to do that, we'll go by cases on the type line we're coercing in. So for example, if we're coercing in a product type, that will step to a pair of coercions in the component types. And something similar will happen for function types. We do hit a little snag here when we get to the path type. And the reason is that as a special case of coercion in path types, we can take a path and adjust its endpoints by some other paths. So that looks a little something like this. I have a path P here going in some direction Y, and then I can take two other paths, Q0, Q1, and by plugging these into coercion in a path type, I can adjust them to get something going between these bottom endpoints. And so intuitively, what that bottom path is it's Q0 inverse followed by P followed by Q1. So you can see as a special case of that operation, we get that paths are symmetric and transitive. So in order to account for that, we'll introduce a second operation called composition, which does exactly that. And then we'll go back and implement composition at every type, again by cases on the type we're composing in. And of course, when we get to the path type, we'll get into a snag again. But in this case, we can close the loop just by generalizing the form of composition a little bit. And so in the general case, the composition takes some term m and a list of equations on dimension variables which describe pieces of that term we want to modify. And for each piece, we give a path to modify it by. So those three ingredients, dimension variables, coercion, and composition, are the backbone of cubical type theory. And then by doing a whole bunch of other work, we can get to see that this type theory is univalent. But all that work is kind of orthogonal to what I want to talk about today, and that is higher inductive types. So as I said before, the kind of intuition for these is that they'll give us a form of quotients for this proof-relevant equality, these paths. So let me start with an example. Suppose we have a type of natural numbers, and then we want to use this to construct a type of integers. And for whatever reason, the way we decide to do this is to have a constructor for positive integers, a constructor for negative integers, and then some equality that says that positive 0 and negative 0 are the same. Well, if we're in this proof-relevant equality setting, the natural way to think of this is as another constructor, a path constructor, which varies in a dimension variable x here, and then we want to attach the endpoints of that path to the things we want to identify, here negative 0 and positive 0. So pictorially, it would look a little something like this. We've got the negative integers, we've got the positive integers, and we've got that segment connecting them. And this concept of path constructors, which are attached to other pieces of an inductive type, is the basic concept of higher inductive type. So we can take that little integer example and generalize a bit from that. And consider the case where we just have any type, and then here A, and then we have a binary relation R on that type. And then we could imagine writing down this quotient type, which has an element point A for every element of A. And then whenever we have a pair AB of elements of A which are in the relation, we draw a path from point A to point B. So that will quotient A by the relation R. But because these paths are proof relevant, the quotient might not behave as you naively expect. So for example, if I take the type of Booleans and I quotient it by the total relation, what I get is not something equivalent to the unit type, but this weird looking type. And so what's happened here is between every pair of points in the Booleans, I've drawn a path between them. In particular, I get a new path from true to true. So I have some non-trivial loops in there. So if I really want to collapse all the structure of Booleans to a point, I can do it, but I need to be a bit more sophisticated. So this is what's called the truncation or -1 truncation type. And like the quotient, it has a point for every point in A. But now this second constructor is recursive. For every pair of points in the truncation type that I'm constructing right now, I'm going to add a new path between them. So how this shakes out is if I truncate bool, I again have these 2 points. And again, I draw a path between every pair of points. But now I can also plug in these new lines I've drawn into the squash constructor. And so, for example, if I take those 2 paths in the middle, I can plug them into squash and get a 2-dimensional path which identifies them. And so that process continues on and on until finally I end up with this big ball of paths where everything is identified with everything else, and that will actually turn out to be equivalent to the unit type. So you can see that we can imagine some more exotic variants of this higher inductive type idea. And so what we want to come up with is a way to describe these and implement them in general. And so there's, of course, been some work on this before. So a lot of that work is in a setting of axiomatic type theory, either starting with ordinary dependent type theory and extending it with some axioms, or considering what properties higher inductive types would have if they did exist. So some of the earliest work is by Sayakova on W quotients, and then there's been a bunch more work on more general schemata, and the most general of which is by Kapustin and Kovac, who you'll hear from later. But these are, again, from an axiomatic perspective, without attention paid to how to compute with higher inductive types. And that's what we're really interested in. And likewise, there's been a bunch of work on the semantics of higher inductive types by de Beer and Monclay and by Lumsden and Schulman, but again, without special attention paid to constructivity. So if we're interested in that side of the fun, we'll turn to cubical type theory. And in that case, there have been a number of examples worked out. And so in the initial papers, and then more recently, Kokan, Huber, and Morberg have given some broader examples and a sketch of a schema. And so our contribution to all this is to give a general cubical schema worked out in detail with a computational semantics. And as I mentioned way at the beginning, This includes indexed inductive types. And I'm going to get back to that later, but let me just talk about the non-indexed case for now. So our schema looks a lot like something you may recognize for ordinary inductive types. A data type is declared by a list of constructors, and each of those constructors takes some number of arguments. And so we'll separate the kind of ordinary arguments into non-recursive arguments, which are of previously defined types, and recursive arguments, which can mention the type we're defining. And as is typically the case, these are constricted to come from some special grammar to enforce strict positivity, so everything is well-founded. And so that stuff is ordinary. And then the new stuff we have here is first a list of dimension variables. So if we have L dimension variables as arguments, then this is an L-dimensional path constructor. And then we have a list of equations on dimensions, either on those argument variables and on 0 and 1, on which we want this constructor to be attached to other things, to reduce to something else. And what we want that to be attached to is specified again by a restricted grammar or language of terms. And so those terms can be recursive argument variables, they can be constructors from higher up in the declaration, they can be compositions, they can be function abstractions and applications. So this is a pretty limited language, but it's good enough for most of the examples we're interested in and not too hard to extend, we think. And so once you write down an instance of this schema, then there's some process by which things like an elimination principle can be derived. And that stuff is notationally pretty nasty, but conceptually not too bad. So what I want to focus on instead is the computational side. And the main question here is, what are the values of a higher inductive type? So let me start with the quotient as an example. So we'll probably expect that the constructor terms are values of this type. So a point term is a value in the quotient type, and likewise a rel term is a value in the quotient type. There's a little bit of a wrinkle here where if we have a path constructor, then wherever those specified equations hold, we want it to reduce to whatever it's supposed to reduce to. But that seems good, set. But the problem we come up against is that we have to make sure we can implement coercion and composition for this type. These are supposed to be implemented for every type. And so in particular, I want to look at composition. And in the case of the quotient, we could have this composition problem. Here we've got 4 points, and they're related with each other in this upper horseshoe shape. And so if I plug that into the composition for the quotient type, it should spit out some value of the type which connects those bottom 2 points. But unless the relation R that we started with here happens to be symmetric and transitive, there's no reason to suppose that such a path exists among the values I've listed so far. So the way we're going to resolve this is by introducing some new values. And what we'll do is have formal composition values, FHCOM, which just sit around and stand for the composition of some composition problem in an inductive type. And the way these will work is they'll be a value most of the time, unless we're at some part of their boundary that's been specified in the arguments, in which case they'll step to that. And so in that way, they behave a lot like the path constructor values. So we'll just stick those in. But now we have something else to worry about, which is, are we still going to be able to implement the elimination? So we've thrown some new values in the inductive type. What is the eliminator going to do with these? Well, what does the eliminator look like? Let's focus on the non-dependent recursor. So it looks a lot like it would for an ordinary inductive type. We supply it with a case branch for each constructor. So in this case, we have 2 cases, one for points, one for rels. And then when the recursor is supplied, one of those constructor terms, it will step to the appropriate case. So that makes sense so far, but then we also have to explain how it acts on formal compositions. Well, we're in luck because the type here, C, that we're mapping into has its own composition structure. And so what we can do is send an application of the recursor on a formal composition to a composition in the target type, C, applied to recursive applications of the recursor. And so essentially, we're using the fact that the quotient has a free composition structure, freely generated. And so if we're mapping into a type which has a composition structure, we can extend a map from the constructors to a map also on these FHCOM values. So that will take care of at least non-dependent elimination. And then the last thing we have to worry about is coercion. And in that case, again, we'll go by cases on the values of the type. And essentially, the coercion pushes inside the constructors. So if we're coercing a point, we'll push the coercion inside coercion A on that inner term. And a similar thing happens for rel. I've elided some of the details here, and the general case is a little more complicated, but that should give you some idea of what goes on. And then finally, like the eliminator, if we're coercing a formal composition, we'll take that to a composition in the target type of recursive applications to coercion. And in this case, the target type is also a quotient. So essentially, we see coercion pushing inside the formal composition. Okay. So that takes care of coercion, composition, elimination, figured out what the values are. I think we're good. All right. And so that approach works for the general non-index case. And now I just want to talk a little bit about the index case. So the kind of primordial example of an indexed inductive type is the identity type, which, as it happens, is the subject of the homotopy type theory axioms. So this is a inductively generated family of types, which has two indices, here A, B, in a type A. And it's generated by a single constructor called reflexivity, which says that this family is inhabited when the two indices are the same. And so if we go to implement this identity type in cubical type theory, we hit a similar problem that we had with higher inductive types, except instead of composition, the problem is now with coercion. So for example, if I have a path P, which goes from M0 to M1, then I can coerce the reflexive identification from M0 to M0 to get a identification from M0 to M1. And again, among the constructor values of the identity type, we don't have anything that accounts for some term of that type. So as we did before, we'll introduce a new kind of value to handle it. And here it's a formal coercion, specifically a coercion between indices. And so we'll add those into the values of the inductive type, and then we'll implement the general coercion by a combination of these formal coercions between indices and the coercion that the type A is equipped with. And so from that, we can get coercion in the identity type family. And we also do have to put in formal composition values, even though there's no higher constructors. And so again, this will generalize from the identity type to all the indexed inductive types you may want, including with higher constructors. And we'll actually be able to show that then the identity type defined in cubical type theory satisfies the axioms of homotopy type theory. So we get that cubical type theory is a model of hot, which is nice. That has been done in sort of a different way by Swan also. OK, so just to summarize, we've given this schema for indexed higher inductive types, and in addition to the examples I described, it includes things like the torus, higher truncations, localizations, and in particular these identity types. And we've given a computational semantics for this, which essentially is based on dimension context indexed pers on an untyped operational semantics. And using that, we're able to prove a canonicity theorem for the type theory. And some piece of the schema for higher inductive types, it's most of the non-indexed schema, is currently implemented in the RedTT proof assistant, so you can try it out now at that link. All right, thank you.
Right, we have 2 minutes for questions. So there's one on Slido. How does your approach to higher inductive types compare to the one of Cocon, Huber, and Mortberg?
Right. So the general setup is pretty similar. There are some differences. The language of dimension terms is different for them than it is for us. And so where we have composition and coercion, they have composition and something slightly different. But the general flavor is the same. But again, ours is worked out in complete detail, whereas they've given a sketch of a schema.
Can you say something about how big the fragment is that you implement, or?
Yeah. So what's missing is those function recursive argument types. So I guess what this is called is generalized inductive types versus ordinary inductive types or something like this. But we don't think it will be hard to do this. It just hasn't been done.
There's one more question on Slido. Does the online decomposition work for reduced product?
I don't know what that question means.
What is the reduced? Oh, OK. Wow. We are already ahead of schedule. OK, one more question.
can you specify values for your higher inductive types without any quotienting? Like, don't you need to say that certain formal compositions are equal to certain constructors?
What will happen in that case is on the boundary of a composition, it will reduce. It's not a value there. I mean, we do have to define these as equivalence relations, but things only get identified with things of the same kind there. So compositions and compositions, constructors and constructors. And the boundary stuff is handled by evaluation.
All right, so let's thank you again.